Welcome to qnawire.
So in this problem, we are supposed to estimate the wavelength for a transition from n is equal to 3 to n is equal to 1 in a molybdenum atom which has an atomic number of 42. And they have already given us the measured value. Let me write this as lambda measured is 0.063 nanometers. Now we use the equation from chapter 37, equation 37.9 and 37-14b, which is basically H times F, or change in the energy is 13.6 electron volt. Change in energy due to the transition of electron from a higher state to lower state, 1 over n prime square minus 1 over n square, where n prime is 1 and n is, not 2, but 3. Now we use, since f is equal to c over lambda, we basically have hc over lambda is equal to delta E. So we have lambda is equal to hc over 13.6 electron volt times c minus 1 square over 1 over n prime square minus 1 over n square. Now this z minus 1 comes from the fact that we have assumed that there is a shielding provided by the 1s electron that is already in the 1s orbit. So the effective charge that the electron which is jumping from n is equal to 3 to n is equal to 1 basically reduced to z minus 1. So after we plug in the values, 6.63 times 10 to the power minus 34 joules second times 3.00 times 10 to the power 8 meters per second over 13.6 electron volt times 42 minus 1 square over 1 over 1 square minus 1 over 3 square and 1.6 times 10 to the power minus 19 joules over electron volt. So basically this joules cancel with this joules, electron volt cancel with this electron volt. So we have, and this second cancel with this second. So we have the unit for wavelength. So basically this goes to 6.12 times 10 to the power minus 11 meters, or 0. 0.0612 nanometers. So this is lambda calculated 0.0612 nanometers, and lambda measured is 0.063 nanometers. So the reason why we did not expect perfect agreement, because we ignored the electron shielding. So basically we had this nucleus, then we had this 1s orbit, we had this 2s orbit, and then we had on the out 3s. So we ignored the shielding provided by the electrons in the 2s orbit. So and we just assume that the shielding is provided by just the 1s, the electron in the 1s orbit. So that's why we had a z minus 1. So because of this, we had this discrepancy in the calculated value for wavelength. If we had instead of z minus 1, if we had considered the shielding by 2s electron in the 2s orbit, then the effective atomic number would have decreased, and which would have caused, so since lambda is inversely proportional to 1 over z, if this has increased, the wavelength, no, I'm sorry, this has decreased since we have z minus something. So if this has decreased the effective atomic number, then the wavelength would have increased and we would have better agreement between these two values. Thank you.